So the basic mechanical model will be discussed by the most simple buckling problem, which is a flexure buckling of a column. This is the simplest one, but all the different calculation types, all the important effects and influences on the buckling behavior of global type stability can be discussed on this model. So this is a simply supported column which is undergo to a flexure buckling, and we have a lateral movement here in the middle due to a half sine wave buckling mode. So next, in this figure, I would like to show what can we calculate on this model and what is to be calculated to determine which is the real buckling resistance of the member, and how the main influences can be taken into account somehow. So first of all, what we can calculate is the Euler load. This is the elastic critical normal force of that column, and this is independent of the lateral movement, of course. This is just one value which is influenced by the cross-section, the stiffness, and the end conditions. And the second one, what we can calculate, is the plastic or any kind of resistance of the most critical cross-section, which is now the middle one. Of course, if we do not have any lateral displacement in this cross-section, the cross-section gets purely compression. So we have the resistance for compression here, but then we have lower and lower resistance for compression due to the larger and larger second order bending moment caused by the lateral displacement of this cross-section. That's why this line takes that form, which decreasing by when we increase the lateral movement. The next important one is the second order elastic equilibrium path of the member of this cross section if we have some initial lateral imperfection. So we start with the amplitude of imperfection here, and then larger and larger displacement can be observed, and this curve is approaching the perfect member, so the elastic critical load of the perfect member, never reaching that. So this is the second order behavior of that member. So up to now, this is purely elastic or purely plastic calculation. If we have both, so an elastoplastic calculation, then we start with the elastic behavior from the initial amplitude of displacement. We start here, and at some point in the most critical cross-section in the middle, plasticity started. The plastic deformation started, and then we have lower and lower stiffness value due to the larger and larger plastic area in the cross sections and along the member, and then we reach a maximum value. This is the elastoplastic limit point, limit resistance of that member, and then we have some post-critical path here approaching the plastic resistance of the critical cross-section. And finally, this is quite accurate calculation type now. And finally, if we consider all the other imperfections, like which is one of the most important, is the residual stress, then we can calculate the real buckling resistance of that member, which contains second order, geometrically second order behavior, nonlinear material behavior, and all the relevant imperfection. And today this is the most accurate way of calculating resistance, global type buckling resistance of steel members. These are the effects which should be somehow calculated. Now the problem is that in a practical design we usually cannot deal with this calculation, even with an elastoplastic calculation. What we have is only some kind of elastic calculation, sometimes only the on the perfect member, so the elastic critical load level somehow, the cross-section resistance, this is again what we have, and sometimes the second order behavior, elastic behavior, can be calculated. And using these calculated measures we should somehow determine the real buckling resistance of the member. That is the design issue. And the two main approach of the Eurocode and almost all structural standards, based on a direct evaluation of geometric imperfection, an imperfect model, or based on some kind of reduction factors or buckling curves. So the first one is called in the Eurocode equivalent geometrical imperfection. What does it mean? This means that we have to calculate only a second order elastic analysis. We have to perform a second order elastic analysis using an artificially augmented amplitude for the geometrical imperfection. The reason is that this is the simplest imperfection type which can be considered in a structural analysis, in a practical structure analysis, and this equivalent geometrical imperfection thought to cover all types of other imperfections coming from the material, from the residual stress, from loading, etc. And if we have this, and this is accurate, then we can hope then calculating the second order elastic behavior of that imperfect member, and then checking only the cross-section with any kind of cross-section check defined by the standard, usually that can be elastic or plastic. Then we get the real resistance of the member from this check. So this is the background of the methods based on any kind of direct application of geometrical imperfection. The second method based on buckling curves or reduction factors. In this case, we do not have to calculate the equilibrium path, even the second order elastic path. What we need is only the elastic critical load and the cross-section resistance, from which we can calculate the slenderness of the member. These measures are calculated on the perfect member or not associated with this buckling mode. We don't have to deal with any imperfection associated with this buckling mode. And then the real resistance is calculated by reducing the section resistance by a suitable reduction factor, which is calculated from the member slenderness. These are the so-called buckling curves which connects the reduction factor to the member slenderness. This is the most traditional way of thinking, engineering thinking about buckling, but it should be noted that all the buckling curves in the Eurocode 3 are based on some kind of imperfect calculation, based on the Itron-Perry formulation. And the Itron-Perry formulation, the basic model for that formulation is an imperfect model. So basically the background of both methods are the same, an imperfect model and calculating the behavior of that imperfect model.